Hi guys, welcome to ENS181 Engineering Mathematics. In this video, we are going to discuss method on solving a first-order ordinary differential equations. Specifically, I will show you how to solve a linear first-order ordinary differential equations. So a first-order linear ordinary differential equation has the form a derivative plus a function p of x times y equals to q of x. So if you have a differential equation in this form, then you are dealing with a first-order linear ordinary differential equations. So the method of finding the solution of a first-order linear ODE is to find the integrating factor I of x. So integrating factor I of x is just equal to e raised to integral of your p of x dx. So this integrating factor will be multiplied back to our differential equation so that it will be easy for us to integrate this equation. So in the final form of your solution, you have this form. You have your y of x equals to 1 over the integrating factor I of x times the integral of your I of x, q of x dx plus c. Or sometimes, they use y times e raised to integral of p of x dx equals to integral of q e raised to p of x dx. Or in short term, the yes pdx equals to squares pdx. So you can also use this one on solving the solution for your linear first order ODE. Later in the example, I can show you why we use this integrating factor on solving the solution of a first order linear ODE. So we have here an example for linear first order ordinary differential equation. So we are going to find the solution for the differential equation dy over dx plus 2y equals to e raised to negative x with the initial condition of y of 0 equals to 3, 4. So first, we are going to identify the value of our p of x and q of x of our differential equation. So we have p of x, which is equals to 2, and our q of x, which is equal to e raised to negative x. After that, we're going to identify the value of our integrating factor, I of x. So the formula for the integrating factor I of x is e raised to integral of p of x dx. So we substitute the value of our p of x, we have e raised to integral of 2 dx. So our integrating factor I of x now will become e raised to 2x. So after getting the integrating factor, we're going to multiply it back to our differential equation. So we have e raised to 2x times our differential equation dy over dx plus 2y equals to e raised to 2x times e raised to negative x. Then distributing our integrating factor, we're going to have e raised to 2x y prime plus e raised to 2x times 2y equals to e raised to x. So to find the solution for this differential equation, we're going to integrate both sides of our equation. So the integral of the left-hand side of our equation, so if you notice, if we are going to get the derivative of our integrating factor e raised to 2x times y, so the derivative of e raised to 2x times y is just equal to e raised to 2x dy over dx, product rule. So we have y times e raised to 2x times the derivative of 2x, which is 2. So we have e raised to 2x y prime plus 2y e raised to 2x, which is equal to derivative of our integrating factor 2x times y. So this part is just equal to the left-hand side of our original equation. So we can substitute this value or this expression to the left-hand side of our equation. This becomes integral of derivative of e raised to 2x times y with respect to x equals to e raised to x integral. So we multiply dx to the right hand side. So we'll get integral of d e raised to 2x y equals to integral of e raised to x dx. So now it is easy for us to integrate both sides of our equation. So this one becomes e raised to 2x times y equals to integral of e raised to x dx is just equal to e raised to x, then our constant of integration c. So to find the solution y of x, we divide all the equation by e raised to 2x. So we have e raised to x plus c over e raised to 2x. Because of our integrating factor, the value of the left-hand side of our equation can now be easily integrated. So, moving on, we're going to find the value of our arbitrary constant. So, we are going to use the initial condition y of 0 equals to 3 over 4. So, the value of our y is 3 over 4. Then the value of our x is 0. So, e raised to 0 plus c over e raised to 0. The value of our c becomes negative 1 over 4. So substituting back the value of our arbitrary constant to our solution, now the solution of our differential equation will be y of x equals to e raised to x minus 1 over 4 divided by e raised to 2x. So this one is the solution for our differential equation dy over dx plus 2y equals to e raised to negative x. We have another example here. Dy over dx equals to x minus y with the initial condition of y of 0 equals to negative 1. So, if you notice, the differential equation is not on the linear form. So, we are going to rearrange this equation so that it will be easy for us to identify the value of p of x and q of x. So, we have dy over dx plus y equals to x. So, now, the value of our p of x will be equal to 1. And the value of our q of x is equal to x. Now for our integrating factor, we have e raised to integral of p of x dx. So e raised to integral of 1 dx. So our integrating factor I of x is equal to e raised to x. So we multiply it back to our differential equation. We have e raised to x times dy over dx plus y equals to e raised to x times x. So distributing our integrating factor, we have e raised to x y prime plus e raised to x y equals to e raised to x times x. Then we integrate both sides. The integration of the left-hand side of our equation, we're going to rewrite this part of our equation, the derivative of our integrating factor e of x times y will be equal to e raised to x y prime plus y e raised to x times 1. We're just using the product rule. So we have e raised to x y prime plus e raised to x y, which is equal to the derivative of e raised to x times y with respect to x. So now we can substitute this back to our differential equation so that it will be easy for us to integrate. So this one becomes integral of d e raised to x times y over dx equals to integral of e raised to x x. So we multiply dx to the right hand side. We have integral of d e raised to x times y equals to integral of e raised to x times x dx. So the integral of the left hand side now will be e raised to x times y. So the integral of e raised to x times x dx, we're going to use integration by parts. So we let u equals to x and v equals to e raised to x. So we have du, which is dx, and dv or v prime, we have e raised to x. So using integration by parts, we have u v prime minus integral of v u prime. So substituting the value of u and v prime, we have x e raised to x minus integral of the value of v is e raised to x and the value of u prime is dx. So we have x e raised to x minus the integral of e raised to x dx is e raised to x, then plus our constant of integration c. Then we equate this with e raised to x times y. So to find the value of our solution y of x, we divide this whole equation by e raised to x. So we have y of x equals to x minus 1 plus c over e raised to x. Now, we're going to substitute the value of our initial condition to find the value of our arbitrary constant c. So y of 0 equals to negative 1. So we have negative 1 here equals to the value of x is 0 minus 1 plus c e raised to 0. So this one will be equal to 1. Negative 1 equals to negative 1. Cancel sila. So the value of our arbitrary constant c is equal to 0. So we substitute it back to our solution y of x. Then our final solution will be y of x equals to x minus 1, since the value of our arbitrary constant is 0. So this is the solution for the differential equation dy over dx equals to x minus y with the initial condition of y of 0 equals to negative 1. So we have another example here, dy over dx equals to 2x times the quantity 1 minus y with the initial condition of y of 0 equals to 0. So first, we are going to rearrange the equation so that it will be easy for us again to identify the value of p of x and d of x. So we have dy over dx plus 2x y equals to 2x. So now the value of our p of x is 2x and the value of our q of x is also 2x. Now our integrating factor I of x will be e raised to integral of p of x dx. To substitute the value of p of x, we have e raised to integral of 2x dx. So the value of our integrating factor I of x is e raised to x squared. So we can also use directly the yes p dx equals to square p dx formula for the linear differential equation. We can also use that one. We have y times e raised to integral of p of x dx equals to integral of our q times e raised to integral of p of x dx. So our e raised to integral of p of x dx is just equal to e raised to x squared. So we have y e raised to x squared equals to integral of our q of x. So the value of q here is just our q of x, which is 2x. So we have 2x times e raised to x squared dx. So the integral of the right hand side of our equation will be, if we let u equals to x squared, then du is equal to 2x dx. We have the value of right hand side of our equation, y e raised to x squared. Then we substitute our value of u and du. To the right hand side of our equation, we'll have integral of e raised to u du. So integral of e raised to u du will be e raised to u plus c. Then we have y e raised to x squared. Then substitute back the value of our u. We have y e raised to x squared equals to e raised to x squared plus constant of integration c. Now, to simplify the value of our solution y of x, we divide all equation by e raised to x squared. So we have y of x equals to 1 plus c over e raised to x squared. So now, to get the value of our arbitrary constant c, we substitute our initial condition. So 0 equals to 1 plus value of our c, then value of our x is 0, e raised to 0. So the value of our c is just equal to negative 1. So we substitute it back to our solution y of x. So we have y of x equals to 1 minus e raised to negative x squared. So we just put the denominator e raised to x squared to the numerator. And then the value of our c is just equal to negative 1. So y of x equals to 1 minus e raised to negative x squared is the solution for the differential equation dy over dx equals to 2x times 1 minus y with the initial condition of y of 0 equals to 0. So in this method, we use directly the formula, yes pdx equals to squest pdx. It's just like a shortcut for finding the solution for our first order linear differential equation. So now we have this practice quiz for linear first order ODE. So I want you to pause this video and try answering the questions. We have number 1, 2, and 3. So that's it for the first order linear ordinary differential equation. So I hope you learned from this video. Next topic will be first order exact ODE. So see you on the next discussion.